Greetings everyone, my name is João Damasceno and I will present the work entitled An Exergy Analysis of Combined Cooling Power System Using Absorption Chillers, a Comparative Approach. The authors of this paper are the engineer Matheus Protásio, me, and the Professor Edson Bazzo. Here is shown the script of this presentation. It's composed by an introduction with a brief history of our laboratory about this subject, the objective of this work, the proposed scenarios, used methodology, results discussion, and finally the conclusions. In Brazil, there are a large potential for utilization of small plants, especially on tertiary sector. This figure shows us the electrical demand in commercial sectors. We can see that in shopping center it's about 54% of electricity is for air cooling. In supermarkets, this cooling in refrigeration demand is about 70%. Due to this high demand for refrigeration, combined cooling power, that is, CCP system, can be feasible for this sector to decrease the costs related with use of energy. Here we have a brief historical record of our laboratory. Hucker 2005 reported an economic analysis of a small cogeneration plant powered by a 28 kilowatts microturbine and a 30 kilowatts lithium bromide water absorption chiller. Rosa and Bazzo 2009 reported a thermodynamic modeling of the power plant powered by a 28 microturbine studied using an ammonia water chiller connected by a thermosiphon heat exchanger. Bazzo and collaborators 2013 reported experimental results considering a heat recovery steam generator where saturated steam is generated using the exhaust gases. So here in LabSat we have a large experience with CCP systems. Now we will talk about the importance of natural gas. According to Calogero 2016, the natural gas has an availability estimate of around 34 years. Today, technology using fossil fuels is more mature than renewable sources, so the natural gas has an important role for supporting the transition from fossil fuels to renewable sources with low cost and easy integration. In Brazil, there is a law project under discussion that treats of the update in the gas market. In accordance to the National Confederation of Brazilian Industry, if approved, the gas production chain will be updated and the product's price would have an expected reduction of about 27%. That way, we reached the objective of this work. This work aims to evaluate four selected scenarios of cogeneration powered by a nominal 1,200 kilowatts electricity prime mover that can be an internal combustion engine or a microturbine, using natural gas as fuel, combined with absorption chillers. Regarding the proposed scenarios, the first scenario, the scenario A, is composed by an internal combustion engine, a heat recovery steam generator, and a steam absorption chiller. The fuel and air are injected into the engine with a nominal power in the order of 1,200 kilowatts. So the combustion happens and the products of combustion with high temperature are sent to the heat recovery steam generator with approach and pitch point of 15 degrees. So saturated steam is generated with absolute pressure of 800 kilopascal. This steam feeds a chiller with nominal coefficient of performance of 1.51. The scenario B is compounded for the same engine than scenario A, but now we have a sensitive heat exchanger. Different than scenario A, we can use the heat available in the engine jacket and the exhaust gas from the engine. So the hot water is sent to the chiller with 95 degrees. This chiller has a coefficient of performance of 0.8. Finally, the water leaves the chiller with 72 degrees. The scenario C is very similar with the scenario A, but the internal combustion engine is replaced by a microturbine with nominal mechanical power of 1,175 kilowatts. The other components of the system looks like the scenario A. The scenario D is very similar with the scenario B, but the internal combustion engine is replaced by a microturbine used in the scenario C. Now we will show the methodology used in this work. So the simplifying assumptions are steady state conditions, kinetic and potential energies are neglected, adiabatic heat exchangers, pressure drop in pipers are neglected, electrical consumption for the thermal fluids pumping is neglected. Other considerations are dead state 25 degrees and 1 atmosphere. The composition of natural gas is delivered by a local dealership. The air-fuel ratio from engine is obtained from catalog. The minimum exhaust gas temperature is 120 degrees. Here we have the composition of natural gas used in this work. The first equation in the right side of the screen were used for evaluate the flow of fuel necessary in the prime movers. The second equation is used to evaluate the cooling capacity, where the COP is the nominal coefficient of performance of the chillers, where m is the mass flow rate of thermal fluid, and the term between parentheses is the enthalpy variation before and after the chiller. In the third equation, we have the thermal efficiency that relates the produced mechanical work and the heat delivered to the chiller with the combustion energy. The fourth equation is the expression for the utilization factor that relates the electricity and the cooling generated by the system with the heat delivered by the combustion. Here we have the input data for cogeneration plant simulation. In the left side of this screen, we have the equations used for the exergetic analysis. The chemical exergy is evaluated using the parameter beta. That is proposed by Zargut and collaborators 1988, and it is a function of the composition of the fuel times the lower heating value also of the fuel. The physical exergy is a relation between the point of the analyzed thermal circuit and the state of reference. The seventh equation represents the exergy balance for calculating the exergetic extrusion. The A equation is the exergetic efficiency, that is a relation between the product's exergy and the fuel's exergy. In this screen, we have the table with the parameters calculation and prime mover simulation. It's important to comment that because of the composition of our natural gas, we have a bigger lower heating value than the fuel of the catalog. That way the fuel consumption is lower. Now we have the evaluated gas parameters: cogeneration thermal efficiency, cooling capacity, utilization factor, exergy destruction and losses, and exergetic efficiency. Among the four systems, scenarios B showed the high thermal efficiency of cogeneration, because in these scenarios we can recover more energy of the combustion. The scenarios with heat recovery steam generator has restrictions related to the pitch and approach points. In respect of the utilization factor, the observed difference in cogeneration efficiency is mitigated due to the high COP of steam chiller, that's bigger than the hot water chiller. And as the flow of exhaust gas in microturbine is bigger, the scenario C is the best choice for this parameter. From the point of view of exergetic efficiency, the scenario B is the best alternative. And finally, taking into account all the results found, scenario B appears as the most technically feasible proposal to meet the demands for code and power for the case under analysis. Finally, we have the conclusions. In this work, thermodynamic simulations were performed in combined cooling and power systems. Four scenarios were analyzed. The scenario B, with engine and hot water chiller, has reached the greatest performance. For further works, the authors recommend the simulation of the other technologies and scenarios to expand the range of possibilities. It is also recommend a more specific exergetic analysis contemplating investigations and each specific component associated with exergy economics. The authors are grateful to CAPES and the Human Resource Program (PRHNP) for the financial support to carry out this research. Here we have the reference of this work, and thank you all for your attention.